let's return to our function where we've used trapezoids to approximate the area underneath the curve. We've discussed how trapezoids better fit the curve of the function than rectangles in a standard Riemann sum. However, most functions are sort of curvy. So one idea that we had was, is there any way to make the top of these segments more curvy to match what's actually going on with our function? And there is. So instead of using a straight line to connect the endpoints from here to here, maybe we should expand our intervals a little bit to allow our function to sort of rise and fall, and replace these two line segments with a parabola, like so. Now we have three parabolas here, which are curvier and seem to be a better fit to our function. If we choose to use parabolas to top our basic shapes rather than straight line segments, we're going to need something called Simpson's rule to attempt to find the area underneath these parabolas. And really, Simpson's rule just comes from using antiderivatives of a parabola, but rather than derive that formula entirely on our own, let's just take a look at it. Simpson's rule is going to require an even number of subintervals on our curve, and the subintervals that we are looking at do in fact align with the subintervals we were using for the trapezoid earlier. The formula for Simpson's rule is a little bit difficult to write down or say out loud, but it has this specific pattern on the coefficients, where we'll be looking at just the value of the leftmost endpoint occurring one time, just the value of the rightmost endpoint occurring one time, and then this alternating pattern of 4s and 2s, starting with a 4 and ending with a 4, for all points that occur in the interim. And for this version of Simpson's rule, we're going to require that we have an even number of intervals. So we compute that sort of alternating coefficient of sums, and then we multiply that entire sum by the width of the subintervals divided by 3. Because Simpson's rule is a little bit difficult to describe or program explicitly, but Excel is really good at recognizing patterns, we're going to hold to the fact that Excel can pick up on this pattern pretty easily. So let's return to our Excel sheet where we computed these values before for the trapezoid rule. We'll get rid of the trapezoid part where we were averaging the different endpoints of the function for computing trapezoids. We've already computed our f of x values, so now let's enter in that pattern from Simpson's rule of 1, 4, 2, 4, 2, 4, 1. Now we wish to take the value of the function and multiply it by that coefficient. So we can create a column for that with a formula. Let's compute this value in this cell multiplied by the value in this cell. We hit enter and let Excel catch on to that pattern for us. And as we did with the trapezoid rule, let's sum these values. Notice that this value is much larger than the value we saw before, but we don't want to forget the portion of Simpson's rule where we take this sum and multiply it by the width of each of the subintervals divided by 3. We can enter in that formula as well. This number multiplied by, in this case, the width of our subintervals is 1, and then we divide everything by 3. And we come up with a value of 53.456 for an approximation of that area underneath the curve. Remembering that we had a value of about 49 when we used the trapezoid rule, we can now see that the answer given by Simpson's rule is somewhat in the ballpark. From our image, it might seem that Simpson's rule is an overestimate here, since we have a decent amount of area above the curve and very little underneath the curve. but in general, this property of fitting curved pieces to our function instead of straight line segments frequently leads to more accurate calculations.